Hi everyone, I'm Alfie. I've just finished the first year of my PhD at St. Andrews, and today I'm going to be talking about some of the work I've been doing this past year about could enhanced structure formation ease some of these large-scale tensions we have in cosmology. So I'll start talking firstly about the tensions I'll cover during my talk, and then I'll move on to some of the simulations I've run, and then the initial results we found. So firstly, we seem to find a link between a local hole, H0, and the deceleration parameter. And I'll also talk a bit about some stuff we've done with bulk flows. So firstly, for this large-scale tensions in cosmology, in the talk title, it says enhanced structure formation. So I should explain what I mean about that by that first. It's basically there's evidence that things in the universe tend to move a bit faster than we expect in lambda CDM, and also grow in mass a bit faster than we expect. So for example, there's the really recent local bulk flows paper, where basically things, the average velocity of things in the local universe is moving much faster than we expect in lambda CDM. There's also evidence for some large cluster mergers that they're merging at incredibly large velocities. So for example, El Gordo, I think, is of order 2,000 kilometers a second, the two clusters are merging at. And then there's also the famous high redshift JWST galaxies, which kind of imply that galaxies are forming quicker than we normally expect. And kind of similarly related to that, and now I have to say thank you for Thomas Shanks explaining this quite well, is that we appear to live in a large supervoid called the local hole. So it's that should be 120 megaparsec by H, I think, but it's on the scale of a few hundred megaparsecs. And we observe it in the entire electromagnetic spectrum. And it's about 20% underdensity to the cosmic mean. As was said before, we don't really seem to form voids like this in lambda CDM. They don't reach this kind of underdensity. So there's an implication here as well that maybe, there's things are moving out of the void quicker than we would expect in order for it to get so underdense. And there's also other evidence that this isn't a unique local phenomenon. So, for example, if you look at the integrated Sachs-Wolf effect, there seems to be a similar overproduction of these around 100 megaparsec voids compared to our lambda CDM expectations. And then the final tension I want to mention is the Hubble tension, which hopefully everyone here kind of knows about. But basically, it's that our early and late time measurements of H0 appear to disagree. The error bars have collapsed around different values, and there's now around a 5 sigma tension there. And there's been some suggestion that this could be related to the local hole. So the scenario would be basically as matter flows out of the supervoid, it creates a systematic enhancement to your local determination of the Hubble constant. So the background value would be the same as the CMB value, but the locally inferred value would be systematically enhanced. So that's kind of what I wanted to look at with this project. So to start off then with the simulations is, how am I actually going to simulate this enhanced structure formation? So basically, we plucked a model from a few years ago called New HDM, which combines Mond gravity with hot dark matter to simulate the enhanced structure formation. And we chose this because it already had been shown to self-consistently produce about 100 megaparsec scale supervoids. But I also want to mention here, this isn't a perfect model. It's not going to replace lambda CDM. We're just using it as a guide for what a better model for enhanced structure formation might do. So for example, it overproduces the small scale structure quite a lot. And so it doesn't reproduce stuff like the observed cumulative Halo mass function. Just so you get an idea of kind of what the different components of this model are. The new part is the Mond interpolation function. And the brief explanation of that is basically you have an acceleration parameter, this A0. When your gravitational accelerations drop below that A0 value, the force of gravity acting on your particles enhanced. So basically it enhances the gravitational force below a certain acceleration. And then the HDM is hot dark matter, which in the original paper was 11 electron volt sterile neutrinos. So we use that as well. And then for some other assumptions, we just assume an FRW background metric and we use the Planck 2018 parameters for the background cosmology. Trying to keep the background as close to lambda CDM as possible. And in addition to running simulations for this new HDM, I also want to, see how the changes in that model lead to changes in the results. So I also ran simulations with lambda CDM, which is Newtonian gravity plus cold dark matter. And then these two other models I've dubbed lambda HDM and mu CDM, which is just the Newtonian gravity plus hot dark matter and the Mond gravity plus cold dark matter. And then something else I want to mention here is I'll talk about vantage points a bit later on. So basically what I mean by that is to kind of probe the observables in the simulation. We split it up into 25 cube smaller chunks, and then you search for a reference particle in those chunks and you measure the observables from them, basically because the particle should roughly correlate to where a galaxy should be. And then finally, just some more parameters for the simulations. We're using a modified version of the Ramsey's code. You modify the Poisson equation like this, basically, to get your modified gravity effects. They have an 800 co-moving megaparsec by h box length and 256 cube particles. And we initialize them at z equals 199 and use Kamen music for the initial conditions, which is pretty standard. And also, if you're interested in what the new HDM model does on smaller scales, there's some paper with some hydrosims came out quite recently on that. So I want to kind of give you an idea now of what's actually happening in these simulations. So the first thing we can look at is the density maps of the simulations, z equals naught. So these are projected through the whole box. And the basic thing I want you to take away from this is left-hand side is cold dark matter, right-hand side is hot dark matter. You can see generically large-scale structure is more prevalent in the hot dark matter models, which is kind of what we expect. And then top to bottom is Newtonian on top and Mond on bottom. And it's just the Mond gravity enhances all structure compared to the Newtonian counterparts. And then a way to understand how the Mond gravity is enhancing things, we can look at the median peculiar velocity growth over time. So the kind of diagonal dashed dot lines in each plot is the Newtonian linear theory prediction for how the median peculiar velocity should grow. And you can see all the simulations fit that quite well at early times. Then there you find this characteristic redshift, which is related to the Mond acceleration parameters. So it's z equals 50 here, where the Mond simulations start, the median peculiar velocity starts to grow a lot faster than the linear theory prediction. And that's basically because the background density of the universe has gotten low enough that it's dropped below this A0 parameter. So it's once you get past, it's once the background density is dropped low enough, that's when the enhancement starts to begin. So the early universe is essentially identical in all these simulations. It's after that point that the enhancement begins. And then finally, just to kind of show what they kind of look like at z equals naught, you can see again, left to right, there's a slight enhancement to the peculiar velocity distributions between cold dark matter and hot dark matter, which again, you kind of expect. And then top to bottom, there's a major enhancement between Newtonian and Mondian gravity. So I've got the local group peculiar velocity as the vertical dashed line here as kind of a reference point. And you can see like the Mond simulations have, I would say, massively over-enhanced the peculiar velocities. So again, I don't want to say these simulations are, these models are going to replace lambda CDM. It's just I want to use them as a guide for what things will look like in an enhanced structure formation scenario. And now to kind of justify why I think they'll be useful for that, we can look at the cumulative Halo mass function. So for the Mond case, you just have to make a correction to convert to the Newtonian dynamical masses, because that's what an observer would see. But you can see, surprisingly, if you compare, say, the new CDM in orange and the lambda CDM in blue, the change in gravity law actually maintains the shape of this scaling relation. It's just the normalization is changed instead. And this is something that kind of carries forwards through all of the rest of my results. And that's why I kind of think these are useful as a guide, because the change in gravity preserves the shape of the scaling relation. It's just generally, it's the normalization or the extent of the relation is extended by this Mond gravity. So that's why I think it will be useful to probe this idea. So the first kind of result I want to talk about is looking at the Hubble constant and deceleration parameter within a local hole. So I didn't mention the deceleration parameter before because it's not really a tension with lambda CDM, but it's a little bit odd. And it's basically, if we use the Planck parameters for a background cosmology, you predict the deceleration parameter to be about minus 0.5. But locally, when we measure it with the supernovae, we find it's actually equal to minus 1.08. Which would imply that the accelerating expansion of the universe is accelerating faster than the Planck background cosmology would predict. So I've got plotted here now. On the x-axis is the locally inferred Hubble constant, and on the y-axis is the locally inferred deceleration parameter. And these, the purple crosses on each plot shows the where the Planck values are, and the black cross shows the locally observed with supernovae. And the colors of each point represents the local density contrast around that point. So you can see you get kind of these bands of density contrast in each of the simulations. It's much more apparent in this new HDM one, but you get bands of the density contrast. So if I now restrict this plot to density contrast, which is near the local Hall density contrast, firstly, in the top left, lambda CDM doesn't produce any local Hall analogs really, which again is we kind of expected. It just can't produce underdensities that large. But if you look at the bottom now for the new HDM and new CDM, you see that this density band related to the local Hall passes quite nicely through the observed point for the local H0 and Q0. So this is kind of the first thing I hope people take away from this talk, is essentially it appears if you are in a local Hall analog and you measure the shoes or the supernovae value of H0, so H0 equals 75, then it appears you recover quite naturally the locally observed Q0 as well, which I thought was quite interesting. So moving on next now to the bulk flows. Basically, for what the bulk flows are, you take a sphere around you, and you look at all the galaxies in that sphere and you find their average velocity. And that's what the bulk flows are. It's just the average velocity of galaxies in a sphere around you. And observationally, of course, we have to do this with line of sight velocities. So I've similarly done it with line of sight velocities in my simulations. And as you can see on the simulations, drop as you increase radius, which is, you know, what you expect. The universe should be homogeneous and isotropic. So if you're in the CMB frame, as these measurements are, then there should be no preferred direction, and it should drop to zero at large radii. And now I'm going to add on the observed curve. And you might see an issue here in that it doesn't drop with radius, it actually increases. And it also increases to 430 kilometers a second at 250 megaparsec by h. And this is like really weird because we should expect it to drop. So why is it rising? And also the like height of the local bulk flow is so large. It's in 4.8 sigma tension with lambda CDM. Like it's really shockingly large. So that's kind of weird that's doing that. Another weird thing with the bulk flows is it looks like they might reverse at even larger radii. So the plot I just showed you, the black observed line, that's with galaxies and it goes up to 250 megaparsec by h. And so, yeah, at 250, it goes up to about 430 kilometers a second. It has this direction in galactic coordinates, L equals 298, B equals -8. There was an earlier study by Mikas Plus in 2021, where they measured 9% dipole in H0, I think about 500 megaparsec by H with X-ray clusters. And they state if this was caused by a bulk flow, it would have a magnitude of 900 kilometers a second. Except the weird thing is it's not in the same direction as the local bulk flow. In fact, it's almost completely 180 degrees reversed. So again, this is really weird because the bulk flows should be dropping, but they seem to be increasing with radius. And also, I don't think a priori it's natural to expect they change direction. So I had a look at that and plotted here. Basically, I took the direction of the bulk flow at 200 megaparsec by h and took the dot product of that with it at 500 megaparsec by h. And you can see it's actually incredibly common in every simulation that the bulk flow is reversed. So -1 here would be complete anti-alignment and +1 would be complete alignment. So every simulation, the bulk flows reverse quite commonly, actually. And you can see the peak is around where the observed angle between 200 and 500 is as well. So that was quite interesting. I didn't expect that. I can also then look at, I know they reverse commonly now. Do they reach the observed magnitude 500 megaparsec by h? Because 900 kilometers a second is quite large. So here, again, on the x-axis, we have the alignment, basically, -1 anti-aligned, +1 aligned. And on the y-axis, the inferred percent dipole in h0 at 500 megaparsec by h. And the red dot represents the MUCAS 2021 results. And as you might expect, lambda CDM, the bulk flows are basically 0 at 500 megaparsec by h, but that's kind of what we expect. That's fine, whatever. But the weird thing is that even in my MON simulations, which I said before are probably like over-enhancing the structure formation, right? Even in that case, they can't reproduce this observed dipole. So that's kind of, that could be a potential issue, I think, for an enhanced structure formation scenario, is it seems like it might not be able to completely explain why the bulk flows, or it might be that you can't use bulk flows alone to explain the Hubble dipole at 500 MPC by h. Something else I looked at just briefly is going back down to the Watkins results now, so within 200 megaparsec by h. I looked at how often you can get a good fit to the rising trend of the local bulk flows, because the rising aspect of it is really weird. So here on the x-axis is the density contrast, the y-axis is the goodness of fit just to the shape. So not looking at the magnitude at all, just the shape alone. And the colors of the points again represent, represent the maximum the bulk flow rises to in that up to 200 MPC by h. And the thing I just wanted to highlight here is you can get about a 2 sigma or better fit to the observed shape for about 2% of the vantage points in all of my simulations. So it's not great, but not terrible. It's better than I expected. It might not be too rare to find this rising shape. So that's kind of interesting. But the other thing is that the maximum that the bulk flow rises to locally tends to be lower if you're in an underdensity. The underdensities tend to be at the lower end of the spectrum of that. And this is where I think there could be another issue with this enhanced structure formation scenario, is that if the local bulk flows would have to be at the lower end of the spectrum, it implies we would need massive peculiar velocities when we go further out to the, past 250 MPC by h when we're entering over densities and stuff. So I think this is something else to bear in mind, is this scenario might require really large peculiar velocities, which I'm not sure would fit with what we observe. So in terms of what I want to do next with this work now, I want to look at creating more complete mock observations, especially for the bulk flows. So the Watkins results, which got up to 250 megaparsec by h, their galaxy catalog becomes very anisotropic and sparse when you go beyond 200 megaparsec by h. So the curve kind of flattens out. So I want to see if I reproduce that when I'm calculating it in my simulations, will I get a flattened shape like that, or will it go up or down? I want to check. And similarly for the MUCAS result for the Hubble dipole, they have quite a sparse sample, I think. So I'm interested to see whether that can push the dipole up or down or not, and see whether maybe that introduces some issues into their results. Also, I want to look at obviously enhancing or tuning my enhancement, to gravity, basically to check if I tune it specifically to reproduce really well one observation, can I also reproduce the other ones fairly well or not? I think that will be an important test. And then also just exploring what other theories do, because as I said, this MOND model it wouldn't be the correct way, I think, of enhancing structure formation, because it massively over enhances small scales. You need something that enhances the large scales, but the small scales stay more similar to normal GR. And yeah, just to conclude, it looks like there's a possible link between H0, Q0 and a local Hall underdensity. The bulk flows commonly flip direction at large radii in all simulations. So the bulk flows flipping direction is not actually an issue at all, really. Yeah, a better theory would be required if this enhancement to structure formation scenario was the correct answer. And then just also, I guess, a general question to the people here is, I was wondering what people think if, what they think about is a local solution to the Hubble tension preferable or not? Because I know there's a lot of models where the solution is to do with dark energy itself rather than local. Thank you.